Hello and welcome to this new video. Today we are going to talk about the fourth extended file system, Htrees, schematics, and more coming up. So yes, today we are talking about EXT4. We are going to talk about the features, the changes, and everything that makes this file system great. Of course, I've made a bunch of video on EXT2, EXT3, and Htrees. You really should watch them in order to follow this video, but in any case, this is a great celebration for the EXT4 file system. So, because I wanted to make this video special, I decided to make a brand new website, maplecircuit.dev, which contains all the schematics that I've used in this video. And it actually allows you to play around with them, so that's a great plus. Now, to be able to follow this video, you are going to need to agree to a couple of rules. The first one is that we're only going to use the 4KB block size in this video. Not talking about 64, not talking about the 1KB block size, none of that. Only 4KB block size. And also, when I talk about data, like kilobyte, megabyte, gigabyte, I'm talking about base 2, meaning that we have 1024 kilobyte inside of a megabyte, right? I'm not talking about 1000 megabyte inside of a gigabyte. That would be a little bit dumb. We're talking about real stored data. The reason why I specified that is because there's actually a real name for whatever I'm talking about, but I'm not able to say it. So there will be none of that here. I cannot say that word. And also, any features that we talk about today will probably not be in historical order. I don't really care about when the features were added, well, apart from the first two, but I don't care about when they were added, I just care about talking about them. So let's get into it, where we go back in time into 2006, where we see that there is a big problem with EXT3. Oh no, what's happening? The big issue is that EXT3 is limited to 16 terabytes of maximum file system size. So you cannot make a file system bigger than 16 terabytes. Now that limit comes because there's a bunch of places throughout the file system which are limited to a 32-bit integer to count the quantity of block inside of the file system. So this limit removes the ability from growing the file system because you would need to add some fields to the block group descriptor table, which in the current form of EXT3 was not possible. So this is why on the 10th of October 2006 with Linux 2.6.19 they decided to release EXT4. Now, how did they manage to change EXT3 to make it accept a larger file system size? And also, what did they add along with it? Because there's two big changes that makes EXT4. Of course, the larger file system size, but also extents, which we are going to talk about right after. Now first, larger file system capacity. For that, we need to look at the block group descriptor table, which is the main place where all the action happened. Now, we can see that there's a couple of changes since the last time we saw it, right? Before it was only the upper part, which contains now a bunch of entries with low at the end. What is that? And why does all of the bottom one have high? Well, this is because we are trying to extend whatever entries are up top with the one at the bottom. So the two are completing each other in order to make the full number. So now throughout the block group descriptor table, we don't have 32 bits of capacity to count the blocks. We have 64 bits of capacity to count the blocks. So that would grow up from 16 terabyte up to 64 zettabyte. Now that's a whole lot of gigabytes. You don't want to count that. So the idea here is that 64 zettabyte is so big, we're not going to hit that, at least not within the lifetime of the file system. So we can ignore the fact that it wouldn't be able to scale bigger than that. Now, let's be completely honest. Throughout this video, we are going to see a bunch of places that means that it's not true that we can get to 64 zettabyte. Technically, the block group descriptor table can get to 64 zettabyte, but there's a bunch of reasons why we cannot get to that value, which we are going to talk about a little bit later. But for now, what you need to understand is they've grown the block group descriptor table, and this change alone breaks compatibility with EXT3. So we need to create a new file system, hence EXT4 is born. Now, the big reason why there's low and high everywhere is because there exists 32-bit EXT4. And 32-bit EXT4 acts a little bit like EXT3, but adds a bunch of features that gives more performance to EXT4. So it's like a EXT3++, or a smaller EXT4 if you wish. Now, in the modern version of EXT4, everybody is using the 64-bit, but before there wasn't really a push to use the bigger version because, well, why would you, right? We don't need that much block. Who is using 16 terabyte? If you're using 16 terabyte of data, you know what you're doing and you're going to enable the right flags, right? But of course, that has changed. So now the default is the 64-bit EXT4, which is the full size that we are going to talk about today. We are only talking about 64-bit EXT4 throughout the video. Now, I've talked about extent a little bit earlier, and we need to talk about them a lot. So let's get right into them. Now, the big idea of storing data on EXT3 and earlier was to actually point everything through a pointer or through an indirect pointer. So we would have the direct block pointers with the indirect, doubly indirect, triply indirect, which would point themselves to other pointers, which would point themselves to a specific block. In other words, every block would need an address to be pointed to them. This is garbage efficiency. The big reason why is because you can get throughout those blocks. It would just happen that you have, oh, we're not reading that specific block, but we're reading the one step further, and we're not reading that one. And it could mean that you have some non-contiguous blocks. And that is really, really bad when you're trying to read off an hard drive. Because remember, if we're talking about 2006, we don't really have SSDs at that point. That's not, solid state drive were not really the thing, right? They were garbage. 2006, they didn't really exist at that point. So that system that we're going to call legacy block pointers, that doesn't work, right? We need something better. And the way that we do something better is by adding a length to those block pointers. Because if you point towards a block and you say, hey, I'm also going to take 1,000 block further than that, those are all my blocks, that will make things way more efficient because you don't have to read 1,500 entries in order to be able to get to your data. You only read one extent, which is what it's called. You read one extent, and now you're able to know all of the places where your data is. Now, the way they achieve that is, of course, by changing the iBlock. So remember, the iBlock is inside of the inode, and the inode is kind of the metadata of your file. So each file has an inode, and your inode has an iBlock, and your iBlock points towards your data. So now at the top of our iBlock, we have an extent header. Now that header is made of a couple things. We have a magic number, which was there to tell which version of an extent it is, but it's not really been changed. After that, we have the number of entries that we have throughout our extent tree, because yes, we are going to use a tree here. After that, we have the max amount of extent that we could have under that tree. And after that, we have the depth of that tree. We're going to talk about that a little bit later. And we have generations, which aren't used by the system. Now, let's look at the extent themselves. What we see is, first, we have the logical block number. Now, the logical block number is the block number inside of a given file. So let's say that we are at the first extent of a file. We would be at logical block number 0 because we are starting that file. If we are 1,000 block into our file, it would be block number 1,000. Now, after that, we have the length of our extent. So there's a little bit of magic that we are going to talk about later, but for now, you need to understand that you have the length of the extent, so how far your file will reach with data that is ours. And after that, you have two pointers towards the start of your data. The reason why we have two pointers is because one is there for the legacy 32-bit EXT4, and the other is there to complement and to extend to the 64-bit. Now, if you're big brain guy, you can see that we don't have a 64-bit system here. We have a 48-bit system here because we have 6 byte, which counts to 48-bit. So where do we get our missing 2 bytes? Well, we don't really get them. We don't get them at all. This is why I told you a little bit earlier that capacity is kind of a lie, right? Because the extents themselves can only reach to 1 exabyte, which is a lot, but it's still not reaching the 64 zettabyte that we were talking about earlier. Now, this again is a lie, and we're going to see that a little bit later, that there's another part of the system which breaks and makes it so we cannot even reach that exabyte limit, but technically extents are limited to 1 exabyte. Now, one information that is good to have is that an extent can point to up to 128 megabyte of data. So it can point to up to 1 full block group of data. 128, same size as a block group, same size as an extent. It makes things way easier to manage. So remember that when we're talking about extent. So right now, because we have 4 extent that can be stored inside of our I block, well, we could have up to 512 megabyte of data inside of a simple extent I block. Now, of course, we want more than that, right? We want to be able to store way more data than that. So the way that we achieve this is by using a good old tree. So remember the depth that we had in our extent header? Let's put it to 1. Okay, let's just step it up from 0 to 1. So what that means in our case is that each extent are going to point to a block which itself will contain a bunch of extents. This allows us to store way more extent inside of our file system than 4, which of course gives us way bigger files than before. So what's important to remember for extent and the file system size is that they were really a big patch onto the EXT3 file system. Their goal was to extend the life of this critical file system. We needed a way to take EXT3 and make it usable, even if you want to add more storage to it. We need to keep our servers alive. Now, with that crucial change where we can now have big continuous chunk of data mapped out by extent, and the fact that we can have way bigger file system, well, we now want more capabilities, right? We want more features out of our file system. We've now opened the Pandora's box, that is, we don't really care about compatibility anymore, because remember, with EXT3 we had the 2 rules. We needed it to be simple and we needed it to be forward and backward compatible. Now, of course, that has been thrown to the trash. We don't have to make it compatible, we don't have to make it simple, so everybody wanted to add their little feature inside of the file system. Now, when I say that they didn't need to make it compatible, there was still a small rule that it needed to be backward compatible, and by that I mean that the EXT4 file system driver should be able to read an EXT3 partition. In fact, the EXT3 driver from the kernel has been completely removed, and it's now only EXT4 that is mounted with a bunch of flag to remove feature. So now if you're trying to mount an EXT3 file system, you're not mounting a real EXT3 driver that's made only for EXT3. There is no code inside of the kernel for that. There is only EXT2 and EXT4. So that compatibility, that fact that the drivers still need to read the old partition, was kept inside of the kernel. And in fact, the reason why they trashed the EXT3 driver is because the EXT4 driver had way better performance. So why use a driver which gives us less performance and nothing for it, right? We're going to use the better driver. So with that change, a bunch of features were enabled with EXT4. One of those was, of course, Htrees. Htrees were now enabled by default. Up to 2-level Htrees were the default. Now, this allows you to have up to 10 million subdirectory inside of a directory. So that's a lot. Before it was 32,000, so going to 10 million is really great, but they still wanted to push the envelope a little bit further, and they went to a 3-level Htree where it gives you 2 billion subdir to your given directory. Now, for that, you need to activate the large directory option, which is not default, but still, it's great that we have that boost. Another thing that they changed is the file system check. because with EXT3, there was a kind of a problem when you would do a real check on the file system. Because remember, we have a journal now, so we don't really have to check the file system often. When we do, it's because something went really wrong. But let's say that we want to force a file system check and actually go byte by byte and actually try to find data and make sure that everything is clean inside of our file system. Well, we need to go from start to finish and read everything in order to make sure the file system is safe. Now, that's an issue because even if you have sections of your drive which are not used, let's say you have a bunch of inodes you're not using for anything, well, the file system checker will still need to look at them because it doesn't know that the next inode might not be used for something. So what they did is they added to the block group descriptor table entries which are used to know if an inode is actually used. So you have an actual offset of the end of your inodes which tell you, hey, the last 1000 inode, there's nothing on it. Don't even try to check them. It's useless. They will all be empty. So this is great, of course, because now when your file system is mostly empty, which, let's be honest, most people, when they have a file system for most of the life of the file system, they're only going to use like 10% of it. So why should you check all of the inodes if they're mostly empty? You're not going to check them now. It's going to run way faster. So now we have an actual file system check that will be faster or slower depending on how much data you have on the drive, which makes more sense and is way more efficient. Now, it's not only the change in the block group descriptor table that gives us that, but it's mainly that of course makes the big change. Now let's talk about allocation, where they did a bunch of change. The first one was to have a multi-block allocator. Now the reason why that's important is because before, if you wanted to allocate new blocks, let's say that you want to write a file and you need to, of course, first allocate those blocks, well, you would need to do one call for each block. So let's just go back a little bit. That would mean that you, to be able to allocate, let's say 100 megabyte, you will need 25,000 calls. That's dumb, right? Because when you repeat the same call, just making the call, not what you're doing inside of that call, but just making the call takes some processing power. So being able to put that big, those 25,000 call inside of one big call, that's of course way more efficient. So they created the multi-block allocator, which allows us to make a bunch of optimization on how we write on the drive. Now, along with this, they also added the speculative allocator, which when you write a file, they will always boost how much they allocate to you a little bit. So if you're writing your file, they will add 8 kilobytes to the end of what you're writing. So if you're writing a big continuous chunk of data, well, you have less chance of having fragmentation, at least for those 8 kilobyte extra that you have. So that allows us to have less fragmentation without any other change. Now, another big change that they made was to have delayed allocation. Now, delayed allocation is something that is standard throughout the file system world. Pretty much everybody uses it. XFS, ZFS, BTRFS, RiserFS, everybody uses it, but EXT3 didn't use it. The way that it works is that we're taking all of those allocation, all of those commands to the drive, and we're just going to wait. We're not going to use them unless we absolutely have to. So there are a bunch of reasons why you would be forced to actually write on the drive, if your memory is full, if your system is asking you to sync with the hard drive. But before that, we're not going to do anything. The reason why they do that is because that way they can take a step back, look at everything that we have to write, and then write in big continuous chunk of data and optimize where you're actually sending the data. So let's say that you would be, for some reason, writing one file for 1 second, another file for another second, and going back to your first file the second afterward. Well, normally you would actually create a bunch of fragmentation because you're switching back and forth. That delayed allocation allows us to take the step back and make sure that we create complete contiguous memory for each file, which makes everything faster, more efficient, and just overall better. Now, one last thing that we talk about linked to allocation would be persistent pre-allocation. Now, I told you when we were talking about extent that there was a little bit of a secret in the length of the extent, is that with that length value, there's a bit at the end that is there only to tell us if the extent is an initialized one, meaning that if it isn't, all the memory that you have under that will be considered 0. Now, the reason why you do that is strictly for pre-allocation. Let's make an example. Let's say that you're downloading your favorite movie. Downloading your favorite Linux ISO using peer-to-peer software. The first thing that your peer-to-peer software will do is ask your file system to pre-allocate. Normally, what that would mean, sadly, for EXT3 is not much. It would at best write a bunch of 0 on the file system to make sure that you have the place on that file system, but not much more. Now, with EXT4, with that persistent pre-allocation, it can ask the file system, hey, do I have this place? And if we have this place, can I reserve it? Can I have it pre-allocate? And with the extent, we can make sure that there's nothing else that will use that place because it will already be used by the extent. But it also ensures that we don't have to write zeros on it, because when the extent is read, if it sees that it is uninitialized, the file system driver, EXT4 driver, will give zeros instead of actually reading what's on the drive. So we don't need to zero whatever is there, and it will only be initialized, it will only be changed when we will write on it, which of course makes things way faster. Not needing to vomit a bunch of zeros on the drive will make it way faster when you only have to say, hey, that's my chunk of data, not actually put data on it. Now, one thing that you might have seen throughout the schematics is that we have a bunch of checksums everywhere. And the reason why is because we now have metadata checksumming throughout the file system by default. It makes things way safer. If you're trying to make sure that you don't have a corruption in the middle of your metadata, well, you need a way to do that, right? And that way is to look at the checksum. And now, because there's a checksum pretty much everywhere, there's a checksum for the super block, for the inode, there's a checksum for intent block, there's even a checksum at the end of directory blocks, which at the end of those directory blocks, they add an entry specifically for checksumming. So they make an entry that is considered deleted, but inside of it contains the actual checksum. So now, because we have that protection throughout the file system, it's way safer, because let's put ourselves into the shoes of somebody that's maintaining an EXT3 file system for a minute. Let's say that that person has a random corruption on their file system. Well, how do you know that an indirect block pointer has been corrupted? Because there's no way to know that, right? There's no place where you can check. The only way that you can know is if it's pointing to a block that doesn't exist. So let's say that it would point to the 16 terabyte block and your file system is 8 terabyte long. Well, of course, we have a corruption there. But if you have a 16 terabyte file system, well, you're screwed, because if you have a corruption throughout your file system pointing to a block that isn't the right one, there's no way to check that data. So that metadata checksumming gives us a bunch more security, because we cannot have a random corruption that won't be accounted for. The only place where you could have that corruption that couldn't be accounted for would be on the data itself, which hasn't changed anything. It was the case before, but metadata needs to be protected way more than the data itself, because if the metadata is corrupted, well, we may lose way more than only one file. Another thing that was added was better time. So now we have more bytes allocated for the use of time. So we now have nanosecond precision, and we also have 408 years to avoid the 2038 problem. So remember, that's a problem that people panicked about, that in year 2038 we will have an issue because the standard Unix time runs out if you don't add a bunch of bytes. That's not an issue anymore. So that's been taken care of by the additional time field, which will use the low-high way of working around. We also have a creation date now, which allows us to know when our file was created, not only changed, modified, but when it was created, when the inode was created, which is a fun thing to have. Now, continuing to speak about inodes, we now have extra space for extended attributes. Now, first, let's just start by saying what is an extended attribute. Extended attributes are a little bit like adding a custom flag to your inode. So now you can add your own values that you can change inside of an extended attribute. So the kernel will have their own couple of extended attributes that are normally not really that used. But if you're using your file system for something a little bit specialized, you may want to have a bunch of values that are way faster to get. Because remember, the extended attribute here are now part of the inode. You don't need to go get a block to get the data. So when you read the inode, you get the attribute, and that's faster. So with that information, you may be able to manipulate the data in the way that you need to, and you may not need to read the data at all. Now, before, the way that it works is it would have a pointer to a block which would contain the extended attribute. And now the extended attribute are included at the end of the inode, where you can add however much extended attribute you want until you hit the end of the space of your inode, which is now 256. Now you can scale that up. Let's say that you would need a bunch of extended attributes. You could scale it up however much you want, but by default it's an inode of 256, so you have 96 extended fields for your extended attributes. Now, while we're talking about attributes, right over that, we can see project ID. Now, those project ID are there to be able to use quotas inside of EXT4. So quotas, as you probably know, is there to limit the amount of reads or write or pretty much anything that you do with a certain file. So you can limit the amount of data that will be used within a file or multiple files using those quota. Now, what is fun here is that it's linked to the inode, and normally it's something that is not linked through the inode but is linked through a directory. The fact that it's linked through an inode makes it so that we can actually point to certain file with more precision. We're not limited to a directory in order to make our choice on who to limit or who not to limit. We can say that exact file I want to limit it, and those 4 files that are completely different at 4 corners of your file system, I can limit them all together on the same quota. Now, another thing that they added to EXT4 was barriers. Now, barriers is something that slows a little bit the file system down, but is there for a great reason. There has been a problem with hard drive that have cache in them. Now, a bunch of hard drives have cache in them. You can see some newer HDD have huge caches, have 512 megabyte of cache in them or more, and that cache is there to try to rearrange whatever writing you're supposed to do and optimize how you actually write it on the platter or when you're actually writing it on the platter. Now that's a problem because let's say that you're trying to write down your data. The first thing that will happen is that it will attempt to write the journal, but now we have a cache. So the journal will go into the cache, and now let's say that it actually writes the data that should have been already written to the journal. Well, you can see where you can have an issue here because it may rearrange the order in which it makes those writes. So it may write the journal entry after writing the data on the hard drive, completely destroying the goal of a journal. So the solution is to have barriers. Barriers are pretty much a way that EXT4 can go talk to the driver of your hard drive and tell it, hey, I'm not doing anything until you write this. Please just write this piece of data before we continue. And because there is a barrier and it won't write anything before the journal is actually written on the drive, well, of course, the journal will be written and then the data will be written on the drive. So that way, it makes sure that we don't have any issue with our journal and with our file system at the small cost of a little bit of a performance loss. Now let's talk about flexible block groups, which is a new feature that is there to attempt to make files a little bit more contiguous. Now, if we look at the standard model for our file system, we can see that, of course, our first two block groups are with a superblock and a block group descriptor table, but the further down we go into our file system, the rarer the superblock and the block group descriptor table backup are there. The reason is that there isn't a superblock and a block group descriptor backup on every block. There is on those block. But there is still a block bitmap, an inode bitmap, and an inode table. Those will take place in the front of each block group. Now, if we're using extent and we want our data to be contiguous, we need a way to remove them, right? We need a way to move them so that all of those are all together and we can have one big chunk of contiguous data, if possible, 128 megabytes of data, a full block group that we can use. So that's why flexible block groups exist. What they're doing is they're taking the bitmaps and the inode table, they're putting them together all onto the block group with the block group descriptor table. So by taking all of those, putting them all in the same place, we reduce the amount of seeking that we need to do in order to get them, first, because they're all in the same place, and second, we allow for more contiguous writing. We can write big chunks of memory without having that little bitmap blocking the way or that little inode table blocking the way. So this is a possibility because inside of the block group descriptor table, we can actually say, hey, the block bitmap is there, the inode table is there, the inode bitmap is there. There is no specific place for them. So by some quick change of code, we can say that the normal behavior when we're creating the file system is actually chaining them all together at the beginning and letting big chunks for writing data. Now, there is one last feature that I want to talk about today, which is meta block group. Now, meta block group are probably the most complex one that we will talk today. I'll try to make it as simple as possible. But there is a problem with standard block group descriptor table, is that block group descriptor table cannot be bigger than one block group. That also gives us a big limit for our file system because we need to fit all our block group descriptor entry inside of one block group being an 128 megabyte. If we do the calculus, that means that we have up to 256 terabytes for a file system given by our system. So we cannot have a bigger file system than 256 terabytes if we limit ourselves to one block for the block group descriptor table. It just doesn't fit. Now, the way that we fix that is we try to break down our use of the block group descriptor table. Let's take 64 entry of our block group descriptor table, which 64 entry end up being a 4K. So that's calculated, right? So let's take 64 entry, let's bundle them together. Let's put them at the start and at the end of those 64 block group that those 64 entry actually control, and let them manage the actual data that's inside it and just repeat that process again and again. So the goal here is to have each meta block group only controlling the data that is inside of them. The reason why you would want to do that is to change the limit, because before the limit of block groups that were possible were due to the maximum size of the block group descriptor table. By doing that quick change, the limit now becomes the amount of entry that we can create of block group descriptor. And that limit turns out that we can have up to 32-bit of block group descriptor, which gives us 512 petabytes of data. Now, this is why I told you that the 1 exabyte is kind of a lie. It's because it's not really written anywhere, but if your meta block group cannot even get there, and if without meta block group you cannot go further than 256 terabytes, well, for sure you're not getting to 1 exabyte, right? Because our hard limit here is 512 petabytes. Now, I haven't dug up if there is any solution to this. I think that they kind kind of knew that at that point people would use something else, and it's true, people will use something else at those scale of data, but the real limit of EXT4, if you're using metablock groups, would be 512 petabyte, because the limit has been removed from the biggest block group descriptor table to the amount of block group descriptor entry that can be managed by the system, which is a 32-bit number, which is up to 512 petabyte of data. So this is pretty much all you can know about EXT4. There is still some things that I've skipped. There's transparent encryption that I didn't really care about that much, and there's multiple mount protection that I don't care either. I'm sorry to whoever made those. I'm sure people appreciate you very much, but I don't. So yes, that's all for this video. I hope you enjoy. Go see maplecircuit.dev. All the schematics are there. I made it as easy to go through them, and you're able to click all the things, and it's fun. It's fun. We now have the most extensive amount of schematics linked to the extended file system on anywhere on the web. So that's a great achievement, right? We've got it, guys. If you want to create your own driver for any of the extended file system, you're going to be able to actually look at something and have some clue what you're doing, and not have to have the mind of Kent Overstreet or Ted So that's like 15 level removed from our brain. But anyway, so I hope you enjoyed this video. If you did, leave a like, subscribe, do all the great things, and of course I'll be back with some more video. I don't know if I'm going to be able to make a video extra of the kernel that's coming up, because that's going to be a lot of work. I'm going to see how I manage it, but for sure the kernel will be there. That's going to be a fun one to do. So I hope you enjoyed, and of course, take care.